Okay, so let's look at question 3. We're asked to calculate the melting point of ice under a pressure of 50 bar, and then to assume that the density of ice under these conditions. So then we're given the mass density of ice and the mass density of water. We're also given the enthalpy of fusion of water. Now you can use the normal solid-liquid boundary and the Clausius-Clapeyron equation, but I actually want to show you that you can use the Clapeyron equation, so equation 4.3, to calculate these kinds of things. So just like for illustration purposes, just so that you also get some exposure to that. So the Clapeyron equation says dP dt is equal to delta Sm over delta Vm, right? And then we say, well, delta Sm is actually, so delta Sm just here on the side, delta Sm is, oh my word, delta Sm is actually, well, you know, delta Hm over T, as you know, so also known as, you know, that where we said the transition entropy is equal to the transition enthalpy over the transition temperature. Right, so we can make the substitution that this is then equal to the molar enthalpy divided by the temperature times the molar volume change. Okay, so this is the equation that we're interested in. So I'm just quickly going to rub this middle part out. Just move that there. Okay. So having that, what can we do with that? Well, we can say approximate dP by delta P and dt by delta T, right? So then we have delta P over delta T is approximately equal to delta Hm over T delta Vm. Okay, so then we have an actual expression from which to calculate physical values, right? Because it's no longer just, you know, differentials, it's now, you know, exact changes, so, you know, so the delta values. So you can plug in a final and an initial value for something. And we can then, so these molar values, so the molar enthalpy and whatever, are valid at a specific phase transition. So because the molar enthalpy and the molar whatever temperature is, so that's molar enthalpy, so this enthalpy here is whatever is valid at that transition temperature. So in other words, if we're looking at, for example, I just wish I can stop doing that. We can then say, so looking at so we're looking at ice to liquid, so we're looking at fusion, looking at the fusion of water. Then delta P over delta T is approximately, I can also fix my T, is approximately equal to the enthalpy of fusion over the freezing temperature. So that's not T final, it's T freezing. I don't really know how to, so just remember that's T freezing, that's not T final, over the fusion molar volume change. Alright, so we actually now have an expression to calculate this change. And we started with the Clapeyron equation. We didn't have to use the Clausius-Clapeyron equation. Alright, But we're interested in the melting point of ice under different conditions, and we're given two pressure values, so we can calculate delta P. We know what the freezing point of water is under normal conditions. We have the enthalpy of fusion. We're given the mass density, so we can calculate delta V. So we can actually calculate, if we can calculate delta T, then we can calculate the new freezing point of water under this new pressure, or the new freezing point or the melting point of ice, whichever way around, using this delta T value, right? So that's sort of where we're heading. So let's make delta T the subject of this equation. So then delta T will be approximately equal to TF delta P. Let me write that more formally as a P. That is a P. And then fusion enthalpy volume. Right. And just as a side note here, what is the change in fusion molar volume, or the molar volume of fusion? Remember, that is the molar mass divided by the mass density of the liquid minus the mass density of the solid. That's because that's the change that we're dealing with. I just want to get to what those values actually will be. So actually we don't need the values right now. I don't know why I just wanted to do that. Anyway, so mass density of the solid, so that's going to be, then we can take out the M communally, and then we can write something as 1 over the change in rho. So we can write it as something like that. So this is then equal to TF delta P over delta fusion of enthalpy M 1 over rho. Alright. Right, so then we just need to plug it in. Then we can calculate delta T. So then delta T is equal to, okay, so TF, T freezing point, so normal freezing point of water is 273.15 Kelvin. I think you can all agree upon that. Then the delta P, so let's quickly just have a note here on delta P. Delta P is equal to, so if we take, we make it, so we define it now such that we have the higher pressure, so we make it 50 bar minus 1 bar, right? So then we just need to remember that delta T will then correspond to the value that we want. So in other words, the T at 50 bar minus the T at 1 bar. Okay, so just remember that delta T then corresponds to that symmetry. So in other words, it's 49 bar, but we don't want to work in bar, we always want to work in pascals. So how do we convert that? Well, that's quite easy. In 1 Pascal, there is 10 to the power minus 5 bar. So in other words, we have 49 times 10 to the power 5 Pascal. Okay, so we just need to plug that in. 49 times 10 to the power 5 Pascal. And then we have our molar mass, right? Molar mass of water, or H2O, has always been around about 18 times 10 to the minus 3 kilogram, because we're working here with joule and whatnot, so then we have to use kilogram per mole. Then nice straight line. And of course the enthalpy is times 10 to the power 3 joule per mole. Okay. So if we're working with kilogram on top here, then we just need to work in kilogram below here. So 1.00, because it's the liquid first, remember it's the liquid minus the solid, because we're working with fusion. So if we worked with melting, then it would be other way around. So 10.3 kilogram per cubic meter. So we can go through that again. So let's perhaps quickly just make a note. Let's do that in red. So rho of the liquid is equal to 1.00 gram per cubic centimeter. So how did I get that to kilograms? In other words, there is 1,000 gram in a kilogram, and there are 100. So just we can actually just, I like to write when I'm doing this kind of thing. I should actually remember always to write it like this. Then you can easily see it. And then we want, there is 100 centimeter in a meter, but we want cubed. So we need to remember that. So how many is there actually? We have here one with 6 zeros. So how many zeros cancel out? 3 3s, so we must multiply by 3. So then we end up with 1.00 times 10 to the power 3. The centimeter cancels out, the gram cancels out, and we're left with kilogram per meter cube. Do you see why I like the block notation? You can never make a mistake when you're using the block notation. Literally cannot make a mistake. Anyway, then over the solids, solid 1, it's the same idea, 9.2 times 10 to the power 3. Okay, 10 to the power 2, because if we used, so it would be 0.92 times 10 to the power 3, but 9.2 times 10 to the power 2 kilogram per cubic meter. And this then gives us a value of minus 0.35 Kelvin. All right. So then if we take the standard so the standard boiling point, so the standard, so in other words, the T at 1 bar to be the 273.15 Kelvin. That means then that T at 50 bar is equal to the T at 1 bar plus delta T, right? Remember that little trick I taught you? So in other words, the T at 1 bar is 273.15 Kelvin minus 0.35 Kelvin. It's actually 0.35 something, but you get the gist. And then you end up with 272.80 Kelvin. And here you might debate the number of significant figures. The problem here is if you round to 2 significant figures, then you're not really going to get the right, you're not going to get a good gauge of what you're working with. So what we're looking here is 2 significant figures after the comma. So that's what I'm working with here. You can come debate me in your personal time on that. Okay. So we see there's a decrease in the melting temperature, which is actually similar to something we saw earlier with the 10 megapascal example, which was way earlier. Okay, so this is something that you can use. You can also use the other equation, of course, but you can also use this method to rewrite the Clapeyron equation and do the approximations. Yeah. The important thing is just basically to remember to, just keep track of if you're using fusion or if you're using the melting, and then you just need to remember to have these things the right way around, and then just use delta T just symmetrically with delta P. You can't use them, opposites with one another. But remember, it should make sense. If you decrease, if there's more pressure on ice, then the melting point should decrease. If there's less pressure on ice, then the melting point should increase. Yeah, it's an easy way to remember that. Okay.